Alpha amino acids contain both a basic group, an amine, and an acidic group, a carboxylic acid, which can combine to form amides, meaning that multiple amino acids can link together to form chains. Depending on how long these chains are, they're known as peptides, proteins, and enzymes, and they can form part of the basis of life itself. Amino acids can also be useful in themselves, serving as inexpensive precursors to other useful chemicals. The most common way of making those chemicals is to remove the acid group. In biochemistry, this reaction is carried out using a decarboxylase enzymes, but it can also be done in the lab. When heated to around 180 degrees with no solvent, amino acids will spontaneously decarboxylate. This is not a useful reaction because they will also decompose messily to form tar, and very little of the desired product will be obtained. Running the reaction in a high boiling solvent and using an oxygen-free atmosphere improves the yield and selectivity. Using a suitable catalyst is better still, as it reduces the temperature required for the reaction to take place, speeds up the reaction itself, and reduces the undesired side reactions. There is some debate about which solvent is best. Barton used diphenyl ether, Kametani used diphenyl methane, Takano used tetralin, and various amateurs have claimed to have had success with high boiling petroleum ether, xylene, turpentine, cyclohexanol, and DMSO. But there are many others who haven't been able to reproduce either those researchers' results or other amateurs' results. From my own experience, I found that the best solvent is benzyl alcohol. It's polar, meaning that reaction is most likely to proceed via an ionic mechanism, and side reactions due to radical formation are kept to a minimum. Having a boiling point above 180 degrees does mean that some thermal degradation occurs, but this is balanced out by the short reaction time. And in this particular case, the fact the final product is soluble in the solvent while the starting material is not gives a clear visual indication of when the starting material has been consumed. The best catalysts for the reaction are conjugated and or aromatic ketones. Other chemistry YouTubers, Chemiolis and Corrosive Chemistry among them, have used acetophenone as both a catalyst and a solvent. Carvone also works as a catalyst. This forms a significant part of the essential oils of spearmint, caraway and dill seed, so it's the most amateur accessible catalyst for sure. Isophorone is even better, being less hindered and not having any other functionalities on the molecule, though it's not easy to find or homebrew. All these catalysts work in the same way, by forming relatively stable amines with the amine group on the acid, turning it from an electron-donating group to electron-withdrawing group, and allowing decarboxylation to take place at a lower temperature. This effect is most extreme with alpha-nitro acids, which readily decarboxylate well below 100 degrees. This demonstration uses an old favourite of amateur chemists, tryptophan, and the reaction was carried out on a scale of 25 millimoles. Tryptophan's a big molecule. A run on my usual scale of 0.1 moles needs an awful lot of solvent, and if it goes wrong, a lot of material has gone to waste. The end product was isolated as a benzoate salt, as this is much more shelf-stable than the free base or the salts of stronger acids. The reagents used were tryptophan, 5.2 grams, benzyl alcohol, 100 grams, isophorone, 0.25 grams, deionized water, 150 grams in total, 85% formic acid, 10.8 grams, perchloroethylene, 20 ml, sodium hydroxide, 10 grams, methyl isobutyl ketone, 80 ml in total, benzoic acid, 3.2 grams, methanol, and isopropyl alcohol, plus tonight's special guest star, a nitrogen cylinder. Tryptophan was suspended in benzyl alcohol and isophorone in a 2-neck flask. The flask was set up for reflux, and the top of the condenser was connected via PVC tubing to a Drexel bottle containing some tap water. This was done so the rate of gas evolution and the progress of the reaction could be visually monitored. The mixture was sparged with nitrogen for 2 minutes via the second neck of the flask, then the second neck was sealed with the stopper and the mixture was heated to reflux. As an aside, isophorone is one of the most pleasant-smelling lab chemicals I've ever come across. It's mostly minty with subtle floral notes. Slow and steady gas evolution began very soon after the heat was applied. As the mixture approached reflux, the mixture turned yellow, the rate of gas evolution increased, and the suspended solids dissolved. After 20 minutes, the gas evolution slowed considerably, and drops of condensed solvent falling back into the mixture released dissolved carbon dioxide with a puff of smoke, causing a good deal of suck back. The reflux was stopped at 30 minutes, and the mixture was cooled to ambient temperature. While it was cooling, it turned from orange to dark brown. While it was cooling, caustic soda was dissolved in 40 grams of water, and the formic acid was diluted to about 10% weight in 100 grams of water in preparation for the next step. Once it was cold, the reaction mixture was poured into a separating funnel and extracted with the diluted acid in 3 portions. More concentrated formic acid is miscible with benzyl alcohol and does not separate well. The combined aqueous extracts were washed with perchloroethylene, then filtered by gravity to remove suspended matter. The filtrate was then basified using the caustic soda solution, causing colloidal solids to precipitate and turn the mixture milky white. The mixture was then extracted with methyl isobutyl ketone, 320 ml portions, and the combined extracts were dried with sodium sulfate and filtered by gravity to remove any water. Benzoic acid was dissolved in 20 grams of MIBK, and once filtration of the extracts was complete, it was added to the filtrate. Nothing happened at first, but on gentle heating, the product precipitated out the mixture as a large mass of white solids. The mixture was heated to 80 degrees, sufficient methanol was added to dissolve the solids, about 10 grams, then the mixture was boiled down until solids started reappearing. This happened when there was about 80 ml of liquid left. The mixture was cooled to ambient temperature with the solid mass forming on cooling, then cooled overnight in the fridge. The product was recovered on the pump and the entrained solvent was washed out with isopropyl alcohol. Tryptamine benzoate was recovered as large clumps of extremely fine white needles, 4.15 grams, 59%, melting point 184 to 188 degrees with decomposition. This reaction is a pyrolysis, which by its nature has a lot of potential for unwanted side reactions, so 59% is a pretty good yield, and the purity is excellent. I've run it several times under these conditions and got about the same yield every time. One lesson I've learned is that the best way by far to get a decent yield is to use a starting material that you can be sure is genuine. Although plenty of amino acids are sold as dietary supplements, they're not classified as food or as medicines, so they're unregulated. I've learned the hard way that supplements are a terrible source for reagents, and in more cases than not, the sellers are completely unaware that the material that they're selling is not what they claim it is, and they have no way of confirming its actual identity. From my observations in various solvents, the decarboxylation reaction is fastest at the boiling point of the solvent, at the point when carbon dioxide can be released alongside the vapours of the solvent. This seems to be true regardless of which solvent is used and the temperature at which it boils. High boiling solvents result in a faster reaction, which is why the reaction in benzyl alcohol, which boils at 205 degrees, took 30 minutes, and the reaction in isoamyl alcohol, which boils at 120 degrees, took several hours. In a 2019 study by Claes, Janssen and De Vos, a systematic investigation of catalyst and reaction conditions was carried out. Although their reactions were carried out in an autoclave well above the boiling point of the solvent and therefore under high pressure, their findings were fully consistent with my own. It was this paper that prompted me to source isophorone and try it out as a catalyst. They found that the best solvents were alcohols at or above their boiling points, and the best catalysts were conjugated 6-membered cyclic ketones. The substituent beta to the carbonyl group had a major effect. Alkyl and aryl groups, which are electron donating, increased the yield relative to cyclohexenone, while an ester group, which is electron withdrawing, lowered the yield. Their procedure, which uses isopropyl alcohol, is also more widely applicable than this one, not being limited to amino acids that are miscible with high boiling alcohols. When I have enough money to source an autoclave in a temperature-controlled hot plate, I will likely try this out myself. But in the meantime, I hope this video brings some clarity to a procedure that is in general poorly and inconsistently documented and even less well understood. I hope you enjoyed it. Thank you for watching.